Hello everyone again and welcome to my channel. First of all, I want to use this opportunity to thank you all for the amazing support, all the like, sharing and the financial assistance you're putting into this channel. That means a lot to us, and we'll continue to do our very best to update you guys on various new videos. And in here we're going to be talking on this particular aspect, the d-electron count relationship with geometries, and we looked at the relationship between oxidation state and that of the d-electron count in various coordination complexes that is linked to transition metals on the periodic table, and we touched on some examples on our previous videos. Now we're going to look at the link between the geometry of molecules to that of the d-electron count geometry, in the sense that we look at this particular notation, which is M, L, X and M, which represents the metal, specifically our transition metal, that may actually lose or gain electrons in the process to actually form a coordination complex with our ligand in here represented as L. And this ligand can have any numbers attached to our metal in here, and the number is represented as this particular subscript, which is X over here. So X represents the number of ligands, and this number of ligands are integer numbers like 1, 2, 3. But in here we're going to focus on 1 because 1 is too simple and it's just pretty much relating to organometallic in most cases. But starting off with X to be equals to 2, well, we notice that first of all they can be found in the D10 state, and the D10 state, which are the ions, like for example we have the likes of copper 1, silver 1 and gold 1. They are all in the same group in the periodic table, and what we notice is that they both share a specific electronic configuration, which is the 4s2 3d. You all will be saying, wait, no, this is not actually the electronic configuration. Actually, you're right, because you have to first fill up this particular lowest energy d orbital, because it's more favorable energetically than to actually have 1 unpaired state in the d first before filling our highest energy level. So what that means as a result of that is that there is a movement of electron from the paired state to the unpaired state to make this low energy level to be paired. So you have the 4s1 3d10. So this particular atomic state of copper in here is actually d11 because we have 11 electrons, and what happens then is that once you lose an electron, what we have is the loss of an electron in the 4s, because this is the highest energy level in terms of ionization, and what we get as a result is a 4s0 3d10. Now what we have in this particular case is that we are transforming our metal from D11 to D10, and D10 will favor 2 ligands attached to them when you have a ligand that is first sterically less hindered, in a way that we have examples like we have the likes of copper chloride, which is negatively charged, or the likes of silver ammonia in here with a positive charge overall, and lastly we have the like of gold cyanide with the overall charge of negative in here. Take note that as you're going down the group, you're increasing in terms of the ionic radius, and what we are noticing is that as you increase in the ionic radius, we are actually getting less likelihood of actually favoring our formation of a less steric state with X equals 2 in there as you move down the group. So in this particular case, what we have is that if you have less sterics in here, on the other start we have more sterics, and for more steric ligands we have the like of a ligand, like for example nitrogen attached to silica, and silica is attached to 3 large groups, like for example methane, and that of phenyl groups in here, not only in this end but at this other end in here. So what we notice in this particular case is that if you interact our ligand, which is this particular case here, and you have two of them in there, to one metal which is manganese 2 with a D5 electron count, and on the other side we have that of iron 2 with a D6 electron count. This actually has a higher ionic radius between the range of 66 and 96 compared to that of iron, which is 63 and 92 in here. But in general, they do have a linear shape that is formed in this particular state over there. X equals 3, and x equals 3 can also be found in the D10 state, which is the likes of copper, silver, and gold, and they both exhibit this particular ionization process going from D11 to D10. And an example of this also is applicable to lead sterics, and the lead sterics example in here is the likes of silver attached to phosphophenol group in here, and you have 3 of them with an overall charge that is positively charged, and then you actually exhibit a trigonal planar molecule in here which is actually favoring D10. However, if you're going for a more steric case, which is using this particular metal with a charge of +3, and you have this ligand which is similar to what we had previously, which is what we did over here, and on this other side we have this over there. What we notice is that if you have 3 of those, we perform or exhibit a trigonal pyramidal, where this particular metal has a D0, so there is no electrons in the D state over here. And that is about it for this particular x equals 3. And finally we have x equals 4, and this is actually divided into 2 geometries. We have the likes of tetrahedral and that of square planar. And in this particular case we're going to see the differences between both of them and look at examples of both of them in here. So first of all, for tetrahedral, this actually favors steric hindrance. However, this doesn't favor steric hindrance. Now, second step we need to take note of is that this actually favors D0 and D10 ions in here. However, this favors a D8 ions in here. An example of this D8 includes the like of platinum 2, we have the likes of palladium 2, we have the likes of this here over here with a +1, and finally we have this here with a +1 in there. So all these, take note, they are actually heavy transition metals, and that is just one of the things you need to take note of in here. Now on this other side here, they actually don't have any lone pair on the transition metal, because if you have a lone pair on the transition metal, then you are more skewed towards the square planar state. So example of this includes the likes of D0. We have this particular example where we have this metal in here which is V, and V actually loses 5 electrons to go from D5 to D0, and on the other side here we have another one which is chromium in here with 4 oxygens. You see that we have 4 ligands attached to this metal, and here we have 4 ligands attached to the metal, but this metal is different from this metal in the sense that this is D5 and this is D6, but they all lose all their electrons. This loses 5 electrons, this loses all its 6 electrons to actually go to D0. So in this particular case, in terms of across the period, we notice that they are actually performing this particular tetrahedral shape across the period. And while on the other side of the eye, looking at those in terms of the category of the same group, like for example these guys all in ions group, with all losing all their 8 electrons, Ru losing all its 8 electrons, and OS losing all its 8 electrons. They are all in the same group. They exhibit a tetrahedral shape in here, and these guys, they are all having a D0 electron count in here. Now, last one in here we're going to look at is the D10 example, and D10 example includes the like of copper 1 losing 1 electron to go from D11 to D10, and you have 4 ligands attached to it, and this has an overall charge of plus, and the other side we have that of nickel, which has an overall charge of 0 but is interacting with carbon monoxide, which is 4. So what we recognize is that while this goes from D11 to D10, well, this maintains its D10. So once you have D10 count in total for each of them, both of them will actually perform or exhibit a tetrahedral shape over here. Now, in this other part here, we have a particular example that is related to platinum, and this is actually related to platinum chloride. All the chlorine atoms that are 4 in here, and this has an overall charge of 0. This actually has a square planar shape with a 1 IR band. Now, on this other part here, once you subject this to 2 ammonium molecules, there is a substitution in here that leads to the formation of a cis-flat compound in here. So on one side we have the cis positioning of our ammonia and the cis positioning of our chlorines over here, and in here we notice that this doesn't have any square planar with a 2 IR band. Now, once you subject this particular molecule again, or complex again, to 2 molecules of ammonia, there's another substitution that leads to the formation of platinum with all 4 ammonias attached to platinum, and then you have a 2 plus overall charge. So platinum in here is PT2 plus, calculating everything in here, and then what we recognize is that this actually has a square planar shape in here. Now, if you do this here and subject this to 2 chlorine atoms, then you have a substitution process that will actually translate this to the trans flat. You notice that in here we have a cis flat for our compound in the first step now. So our trans flat will actually have this particular shape where the ammonia is trans to that of the chlorine atoms, and what we realize is that, hey, we lose our square planar geometry in this particular process over here. So that's about it for this particular examples and the first step in here, going from x equals 2 to x equals 4. On our next video, we'll talk about x equals 5 to x equals 8. All the same, thanks for following me through this long video. I truly appreciate it. Hit the comment down below. Let me hear your thoughts. Hit the like, share, and subscribe. Your support is truly appreciated. And talk to you all later. Be smart.